Okay, this is lecture 19, a special lecture for memory devices. So, lecture 19 is for memory devices. Our previous lecture, lecture 18, was for MOS capacitor. It was the very first lecture on MOS capacitor because until then, we spend our lecture hours for PN junction or device physics. But why lecture 19 is for memory devices? It is because I have to take my business trip to international memory workshop. Actually, it will be held in Seoul. However, I have no time to make the on-site lecture. So that's the reason why today, on Friday night, I'm now recording this lecture 19. Okay, then May 15 will be a holiday in Korea. So our next lecture, lecture 20, will be made on May 20. And in that lecture, I will continue to consider the MOS capacitor. That is quite an important topic in our one. And today's recorded video is just for a special lecture. So because I'm now taking the business trip. Okay. So please note that we are just starting discussion about MOS capacitor. So actually, the lecture contents in today's lecture is not very suitable for our current lecture progress. However, since this course is not for junior level students, but for senior level students, I assume that actually you know about the MOS transistor. That's the reason why I still try to explain something in this lecture. So, in order to understand this lecture, we must first understand the operation of MOS transistors. Yes, however, still we are in the stage of MOS capacitor. It's a very initial stage, so it's not that good, but please treat the MOS transistor as a switch controlled by gate voltage. Here we have a symbol for MOSFET, and here we have a gate. So if a gate voltage is higher than threshold voltage, then we think that here we have a channel and these two terminals are connected, electrically connected. So please understand this one. So let's go to the various types of memory devices. Okay, although our title for today's lecture is memory devices. However, I will today just consider DRAM devices. My original plan was to consider all of three major commercialized uh, memory devices, but due to time limitation, I have to stick to the DRAM only. Yes, so I will explain later. But before talking about these ones, so I have to say there are also new memory devices not as popular as this SRAM, DRAM, and NAND, but there are many other memory devices under active research. So let me name them. For example, this one, FERAM here, FE means ferroelectric. So, nowadays ferroelectric material gains a lot of research interest worldwide, and ferroelectric material can be used as a storage material. So it has certain domain, and yes, for example, this one or that domain, ferroelectric domain, can be written and that can be led by electrical operation. So there is a certain attempt to make FREE. This is relatively new. Yes, they are all new compared with these old devices. However, I think that this is one of the newest one or getting the most recent research interest worldwide, and other three relatively older than ferroelectric lamp. Here we have a PC lamp. PC here means phase change. So phase change means that if we conduct certain current to this one, then this material is just melt and change its phase from amorphous or crystalline. So therefore, depending on its phase, it can show sometimes high resistivity or sometimes low resistivity. So by using that property, this PCRAM gives us certain differences in resistance, and just measuring the resistance, we can say that one is logical 1 is written or logical 0 is written. That is the PCRAM. And we have other two here. Here we have MRAM and RRAM. So MRAM is that is a magnetic. So depending on its operational principle, we have some different specifier in front of this MRAM, but basically it means that in between two terminal contact, here we have a certain layer of a magnet, and also by applying certain voltage or conduct current, we can switch the spin polarity of this one, this magnetic part. So then if that is aligned or not aligned, oppositely aligned, depending on their alignment, also we can achieve high resistance or low resistance. So that is way of MLAM is operated. Finally, here we have another lamp called as RLAM or RLAM. So here RE is corresponding to resistive. And everything shown here are actually resistive, but here resistive means that usually also we have a two-terminal device, and in between we have a certain material. And sometimes, of course, there are many different mechanisms. However, for example, we can make a certain current conduction path between these two contacts or terminals. After that, here in this part, if there exists further current conduction path, then it will show low resistance. Or if we can just eliminate these current conduction paths, although we have a current conduction path up to here, but since this part is missing, so the measured resistance will be also show high resistance, high value. So quite similarly, we can also achieve this high resistance and low resistance. So now you can understand in many cases these Of course, in the case of every lamp, we have many other uh, possible operations, but at least these three devices just provide us relative change in measured resistance. So basically, it is a two-terminal device. Yes, two-terminal device, and when we apply certain voltage difference, then there will be certain current conduction, and from this ratio we can estimate R, and in this case we can find high resistive case or quite a small low resistive case. So say that one of them is logical 1 and one of them is logical 0, then we can distinguish two different states, so that is regarded as a bit. Yes, that is the common way of this kind of new memory devices. Okay, however, when you come back to our more conventional and traditional memory devices, all of them are based on not a resistive component, but they are all based on MOS transistor. So let me explain one by one. Okay, so today's main topic is DRAM. So I will explain the structure and some consideration and operation of DRAM devices. But let me just explain a little bit further about other two ones. So SRAM will have a um, separate page, and here we have and so okay. So I will talk about NAND. So in the case of NAND, how can we write a certain bit into this NAND? In the case of NAND, we have a transistor. Here we have a transistor. This is let's say this is a typical transistor, and here we have a gate, and here we have a source, and here we have a drain. So that is the typical setup of our transistor, but instead of that, in this special technology NAND, here we introduce a special step. So still this is metal. However, previously it was just an insulating layer. However, in the case of NAND, instead of this fully dielectric material, we intentionally introduce a certain charge storage layer. Yes. So typically, what is it? Nowadays, silicon nitride is used as a charge storage layer. So when we apply very high gate voltage, if the gate voltage is too high, then of course we will have some electrons here collected by the inversion property, inversion phenomena. After that, these electrons can overcome the potential barrier between silicon and silicon dioxide. Yes, we have learned that difference, the barrier height is about 3.1 electron volt. However, since we have applied much higher voltage, even that high potential barrier can be overcome, and electrons are just stored in this silicon nitride layer. Then, since we have a certain negatively charged electrons in this part, actually the threshold voltage of this device is increased. So then, when we try to at a given lead voltage, when you apply uh, the read voltage to the gate voltage, then the current obtained from this structure will be significantly reduced. So we now understand, oh, some electrons are stored in the storage node. So we have to say that this is not something and another different logic state. So here, let me just summarize my discussion about NAND. In the case of NAND, we have a silicon nitride layer to store our data. So this specialized one is used as a certain room for storing our electrons or releasing it. So based upon that amount of charge stored in that silicon nitride layer, we distinguish the logic levels. Okay, so I quickly covered the other ones, and now we have two other ones. So let me just go to the next page to describe the SRAM. Okay. Oh, before talking about the SRAM specifically, we have to say the array of memory cells. So um, today, more or less, we will talk about just one bit cell structure. So the very basic elemental unit to store 0 or 1. So, however, we want to have a high capacity for memorizing something. So therefore, instead of having only one component here, we wanted to make a certain array of memory bit. So it can be done by in this way shown here. We just make an array, and if we wanted to, for example, select the component shown here, then we just select this horizontal line, typically called as word line, and this vertically aligned line, bit line. Then this combination of word line number and bit line number uniquely select one bit cell. So therefore, if we have, for example, W word lines and B bit lines, then total amount of bits we can store in this array will be just a product between them. Then how can we select one of them? For example, if we provide address of a certain word line, then here we have decoder. Then by using this decoder, only one word line is selected. Selected means that its voltage is getting higher, and all other are just set as 0. So that is the typical way we select one thing. So word line, select word line. Also here we have binline drivers to connect it to the bit line, and also we can select certain bit line. So by combining these two information, so word line number and bit line number, we can arbitrarily select any component. Okay, so that is the array. So if we have large array, then it is certain that we have more capability store more bits. So it is always good news. However, depending on the technology or depending on the type of memory, the area has a certain limitation. So of course, we wanted to have small dimension, small area bit cells. However, it is not always possible. Okay. So before talking about today's main content, DRAM, but let me just cover our SRAM. So RAM is random access memory, and in a RAM we can just specify certain word line and bin line and select anything. So without waiting for a long time, sequentially accessing all kinds of information. So we can directly select go to that address. And here, difference between SRAM and DRAM is its first specifier. Here, static, and instead of that, if we say dynamic, then this becomes a DRAM. So then what is the meaning of static and dynamic? So it is related with that property. In the case of this static RAM, so SRAM, if we write once a certain information, for example, yes, this bit is 1, then when before we turn off this device and shutting down that device, the power supply is gone, then this 1 is still remaining as just 1. So once we write something, then we don't have to care about it before we read that one. However, there is another type of device, something like this. Write 1. And for a long time, for example, 10 seconds has been passed. After that, when we try to read it, then actually it may be just 0. So I mean that the data written in the DRAM just survive only for a short time. So it sounds really weird because we are now talking about memory. So memory means if we say something, then that should be there. However, in the case of DRAM, there is a finite duration, limited duration for memorizing it. So therefore, before it forget everything, we have to remind once again, okay, you had 1, please refresh your value again 1. And before it forget once again the memory 1, then we have to visit, and you are number 1, logical number 1, so you must remember it. Frequently and periodically we have to remind this guy DRAM to its present value. So sounded really weird, but this is DRAM, and SRAM has no need to be refreshed. So that's the reason why here we have the terms like dynamic and static. Here dynamic means that every time we have to dynamically refresh and restore the data. Okay. So then how can we implement SRAM device? That is a long story. So if you are interested, I want to recommend you to watch my previous lecture video. So this is the title of that video. Actually, that was done in the last December, and at the beginning of that video, I just tried to explain in general concept, not directly related to the SRAM. So please start from 35 minutes, then you will see you can directly jump into the discussion about SRAM. But let me just summarize this simple manner. I want to summarize the SRAM part. It is just given as 2 cross-coupled inverter. So if this number is logical 1, then by action of this inverter, here we have logical number 0. And if this is logical number 0, then by action of this inverter once again, the output is also logical 1. So simply speaking, here we have two different inverters. However, they are in agreement for these output values. Both of them are quite happy because in this case 0 is input and 1 is output, and for this case 1 is input and 0 is output. Yes, that is actually the operation of our inverter. So once it is placed in this 1 0 configuration, then without any further external perturbation, that will be just stay there. Also, we can find another stable state like this instead of this one. Of course, we can say this is 0 and this is 1. Also, it is quite much preferable for our two cross-coupled inverters. So, if we just by some way write down certain number, certain logical value here and there, then if we provide power to these inverters, then its value will be kept as before. So that's the reason why we have SRAM. So up to now, I just explained this core part, two cross-coupled inverters, but how can we read and write something to this one? So in order to access to this data node here shown here and there, we have to introduce a certain electrical path toward our bit line here. So in order to connect this bit line and our storage node, actually we have to introduce a certain transistor. So in this transistor is controlled by our word line, or yes, this is controlled by word line. So by selecting the value of this word line voltage, we can sometimes connect these two nodes or sometimes disconnect this node. So once we write something and when we want to just take it and keep this number, then usually we apply gate voltage of this word line, or word line voltage is kept as 0. Then electrically, as I told you in my previous slide, so today we can just treat this transistor as a simple switch, and if gate voltage is lower than threshold voltage, then actually this transistor is working as a disconnected line. So let me just come back. And when we apply just 0 volt, then electrically this MOSFET does not play any role, so it is just kept as its static value. But when we apply, for example, equal to VDD, then now these two nodes are just connected. When in the case of read mode, here we have where maintained value. So this inline voltage is affected by this storage node voltage. So it shows a different values once after this word line is biased to VDD. Okay, this was quite a simple explanation. So in order to make it dual, so we also provide another access transistor. So here we have another one corresponding to bit line bar. Yes, so detail can be found in this one. So now let's go to our main discussion, the DRAM. Before starting our uh, discussion, so we have to understand, although DRAM is so widely used, but it was just invented just several decades ago. Uh, Actually, the first patent about the DRAM was registered in 1968. It was coined, the idea was appeared in 1966 and took 2 years to be really registered. And it was invented by Robert Dennard, the inventor of DRAM, and he passed away just a few weeks ago. So it was a great loss to our society. And anyway, so although everything seems to be quite well established, or everything seems to be just given to you, however, there are some guys actually invent something and contribute to the society. So maybe we have also such a chance to contribute in this way. Okay, so now let's go to this slide. Here you can see that 1T10. So I made a mistake. So sorry about that. I made mistakes. 1T16. Sorry about that. This is the structure, the universal structure of our DRAM cell. Here, in order to represent our 1 bit, we need only one transistor and one capacitor. That's it. So let's come back to our SRAM case once again. If we come back to our SRAM case, now you can find that we need two inverters and two access transistors. So two access transistors are corresponding to this one, and two inverters representing these guys. And each inverter needs two additional transistors. So overall, the sum is 2 times 2 plus 2. So we need 6 transistors in order to statically store 1 bit. But when you go to this way, then actually you can see that the number of transistors is just reduced to 1. Of course, we need one specific capacitor. However, in terms of area, it is much more efficient than the SRAM. So that is the main reason why we use DRAM. Although it should be periodically refreshed, however, sometimes storage capacity is the most important thing for certain application. So that's the reason why, although it has certain difficulties for like a more complex circuitry to maintain this kind of refresh job, but we need this DRAM. So DRAM is good for capacity. Please understand this one. So it is considerably smaller in silicon area than a CMOS SRAM cell. Okay, then here we have a capacitor. So if this V V node voltage here is equal to VDD, then we are saying that it is corresponding to logical number 1. Or if this V node is quite close to voltage 0, then we say that this is corresponding to logical number 0. Okay, so it is quite easy to understand. So simply, if we store charge, positive charges here, then this state is corresponding to logical 1. And if we don't have any charge stored here, then it is corresponding to logical number 0. Okay, then it was the capacitor story. And now think about this transistor. Here we have a transistor, and usually this transistor is made of N MOSFET. So what is N MOSFET, P MOSFET? You don't have to worry about it. So just treat this is a switch turned by this gate voltage. This is a gate, and this gate is connected to the word line. So word line voltage is actually gate voltage of our transistor. And bin line runs vertical way, and here we have a bin line voltage, but here we have a ending character T, so it will be clear why we have this distinction. So, if you just think about this one, if we have, for example, 0 volt for our word line voltage, then what will happen? Just similar to the case of SRAM, actually this MOSFET does not connect these two nodes. So therefore, ideally, so the stored charge here will stay forever. So I mean that once again, let me just think about this one. When it is VDD, we have a charge. So we have a positively charged particle, negatively charged particle, and here we have the transistor whose gate voltage is equal to 0 volt. Yes, and here we have, of course, bit line. Then, since here gate voltage is equal to 0, if everything is ideal, then this transistor will not conduct any kind of current, so electrically it is just disconnected. So it is corresponding to just one case like this. Here we have some values corresponding to VDD, and charge is collected and nothing more. It is just disconnected. Then what will happen? The charge will stay forever. However, here we have to consider the reality. Although we apply 0 volt to this transistor, unfortunately, this transistor can conduct a small amount of current. So now we may have a small amount of current between this bit line and our storage node. So after some time later, we find that actually the amount of charge is reduced. If we wait a little bit longer, then we will lose more. And time elapses, then we will lose more and more. After that, okay, long time has passed, and I want to check the number of charges stored here. Then we found that actually there is nothing, no additional charges stored in the capacitor. So what happens? The happening is just here we have a leakage current, and this leakage current demolishes our stored bit. So that is very important understanding on this case. Okay, so capacitor. Here we have a capacitor. The device is quite simple, and its capacitance nowadays, in these days, around have a value of 10 femtofarad. So I just took it from relatively old conference paper, but I think that this is good enough to understand the historical progress of a DRAM cell. So when it was first invented, it was just implemented with planar capacitor. Here, where can you find the transistor and where can you find the capacitor? So this part is corresponding to our transistor. So this is a gate and this is connected to our bit line and this is corresponding to our storage line. Then where can you find the actually capacitor? Yes, this one is corresponding to our capacitor. So this is storage node and capacitor, and here we have a grounded plate. That was the planar capacitor. However, in order to supply sufficient amount of capacitance, actually we have to introduce very wide capacitor. So please note that the main driver for this DRAM development is its a small area compared to the S-line. So therefore, it is not very good to have this kind of a planar capacitor. So DRAM has evolved two different types, mostly depending on the capacitor. Here, the upper side, we have stack capacitor line, and here we have trench capacitor line. So in this case, first of all, we make a certain trench here, trench. After that, first we generate a certain capacitor. After that, transistors are made. However, in this case, it is very difficult to align our capacitors and transistors precisely. Also, if something is wrong in this capacitor, then it is very difficult to detect that problem. So it was not very successful, and these days every DRAM company are fabricating their DRAM following this kind of line. So you can see that here still we have a transistor and transistor and transistor, and instead of the same transistor we have a variety of capacitance. So here we have a capacitance. Instead of this planar one, now our capacitance can found in this one. So although we have a relatively small footprint, but it is not just flat and it has its curvature, so we can increase the effective width or effective area of this capacitor. Also, you can see that this multi-pin one, so also you can find that there is something like this one, this one, this one. Yes, so still we have a relatively small footprint, but we can just integrate more and more capacitive component into this cell. And eventually it has evolved to the cylindrical one. So now we have very tall billing corresponding to the capacitor, and its aspect ratio is nowadays several dozen. Uh, so it is like a very tall billing in its structure. Okay, so capacitor is quite important and it has evolved. And most important thing is a capacitor requires a lot of silicon area. So in this DRAM scene, the most important thing is silicon area consumption. So reducing the silicon area consumption is a far most important topic. So that's the reason why uh, our transistor, our structure has been changed in that way. And another one, although we have not talked about this transistor, nowadays we have also quite much specialized structure for this transistor. Of course, when we come back to our previous discussion, the most important thing in this data storage is to reduce the leakage current. So how can we reduce the leakage current? One way is make a long transistor. However, still we wanted to keep this footprint as small as possible. So therefore, instead of making this just a planar transistor, instead of that, we introduce such kind of current conduction path instead of this direct conduction path. So by applying such kind of curved structure, we can effectively increase the gate length without sacrificing silicon area efficiency. So that was also an important uh, change. So anyway, then now let's go to the operational part. How can we write our data into the storage node, capacitor voltage, and how can we read that stored capacitance or charges from that capacitance? Okay, so let me just explain it step by step way. First of all, it is straightforward to write logical value 0 to a DRAM cell. Then how can we do that? Here we have bit line. At bit line, if we wanted to write 0, then this bit line is biased to 0 volt. And here we have access transistor. Once again, and this access transistor is just turned on. Okay, now it is turned on. Then here we have a certain capacitance. Let's say that previously we had certain charges, but if we have this kind of configuration, then of course its voltage will be higher than 0 volt. So these charges will be discharged through that current path. Then after short time later, these stored charges are all gone. After that, it becomes just 0 volt. So right number 1 is quite easy. Just to open the gate, then this 0 volt will be copied into this capacitor. So that's it. And now consider writing a logical value 1. Maybe you think that it is not that difficult once again. So just bias it to VDD. Okay, good. Then now when we apply this voltage, then now let's say initially let's say this was nothing, 0 volt. Then what will happen? Here we have a low voltage and here we have a higher voltage. So we will have a certain current conduction. So due to this current conduction, some charges will be stored in this capacitance. So we can expect that this storage charge is increasing, and increasing as time being. Good. So therefore, if we wait a long time, we may expect that eventually that value, the value will become just VDD. But unfortunately, please think about this one. Our transistor is regarded as a switch when the gate voltage is higher than threshold voltage. Then our transistor is regarded as turned on. So it means that if gate voltage, or more precisely, the voltage difference between gate and its source voltage is equal to threshold voltage, it is no longer turned on. So simply speaking, let me come back. So if we have this kind of naive implementation, then although this storage voltage is increasing, but when it becomes VDD minus VT, then what will happen? Now this transistor is just having VT as a gate to source voltage. So in this time, this transistor becomes inactive and just turned off. So if we apply just water voltage equal to VDD, then our maximum expected value, storage value, will be just VDD minus VTH. So in order to compensate this effect, instead of this VDD, so we apply certain voltage at least higher than VDD plus threshold voltage. Then now it has still certain margin, so we can increase our voltage up to VDD. That is explained here. So we have to apply slight boosted voltage to our watt line. So after storage node is fully charged or discharged, means that fully charged means we have written logical number 1, or fully discharged means that if we write logical number 0, then quite obviously the watt line is brought back to its standby voltage, for example 0 volt. So now it is once again turned off. So as we have already discussed in our previous slide, if we have VDD as a stored value, however, after time being, then this VDD will decrease. So before completely losing this storage charge, we have to restore its value again and again. Okay, but anyway, for a short time we can store that information. So that was writing operation. Then now let's go to the read operation. Well, read operation. However, in read operation, we need two different things. One is of course read. However, another one is we have to recover our present value. Otherwise, this signal becomes weaker and weaker, and eventually it will disappear. So in order to do that, our read operation is quite important. So although it is not drawn here in this part, so we have a sense amplifier, and it detects the difference between this BLT line and VLC line. What is VLC? This is the reference one. So it is not connected to the selected bit. So it means that it is just showing the reference value not affected by the storage node information. So by considering the difference between this BLT voltage and BLC voltage, then we can detect its value. For example, let's say that if we have the case BLT is higher than VLC, it suggests that, oh, our previous node voltage was maybe close to VDD. And if we have VLT voltage is lower than our reference voltage, then maybe we can say that, oh, original value stored in the capacitor was just 0 volt. That small change is sensed by this sense amplifier. So by using that the detected difference, then we can determine whether this is 0 or 1. Okay, in order to make such kind of a comparison, then actually we have to have a neutral initial value. So whether it is VDD or whether this is 0, how can we make a certain criterion for this discrimination? So maybe you will see that just half VDD is a neutral value. So we start from this neutral value half VDD, and if BLT voltage is becoming higher than this value, then it means that our original stored value is logical 1. And if it goes to below half VDD, then we can see that the original stored value is just 0. Then maybe you can say that, why don't you just introduce a separate, very accurate reference for VDD? But you know that this is not a fair comparison because there are many other components to reduce this voltage. So this VLC is very similar to this BLT, and only difference is whether that is connected to the selected bit or not. So by using this BLC, we can make a fair comparison for that node. Okay, so now you understand. Taking the difference between these two bit line voltages, we can have something. But please think about this one. Let's say that previously we had something corresponding to VDD, and originally it was biased just half VDD. And when this borderline voltage is highly applied, then these two nodes are connected, and some charge, because this VDD is higher than half VDD, some of our stored charges are just moving into that part, so increasing the BLT voltage and also reducing this node voltage. Okay, that is quite simple. Then now in this sense amplifier, we now understand, okay, the original value was VDD. Then at that time, how about the voltage stored in V node? Is this still VDD? Of course not. In order to increase this bit line voltage, actually its value has been already quite much reduced, and it is not a strong value, logical value 1. It is quite close to neutral value, half VDD. So by reading the information, already our original information was demolished. So what we have to do is once again recover this lost value. Now we know that value, we must write 1, but how can you write 1 once again to this point? So that is done by our sense amplifier. Okay, this first paragraph, it is corresponding to the read operation. We just apply sufficiently high boosted word line voltage. Then when one bit was stored in the cell, then our B90 voltage will be above half VDD. So we have already explained that one. After we have a sufficiently large differential signal, then sense amplifier is activated. Then what is the sense amplifier? It is once again just a cross-coupled inverter. But before starting its activation, so it was just turned off. So it was connected to BLT voltage and let's say BLC voltage. And since it was turned off, nothing happens. Actually, this point, these are just disconnected. However, after some time later, now if we have certain difference between BLT and BLC, then sense amplifier is suddenly turned on. Then it detects small difference. This small difference is actually exaggerated by this feedback loop. So initially this BLT was only slightly higher than BLC, but eventually it becomes just a clear logical value 1 and it becomes clear logical value 0 by action of this cross-coupled inverter. So by action of this sense amplifier, we can restore the original value of B node, and it is called as refresh. Okay, so here we have some discussion about the lead signal. So lead signal here means that the difference between our BLT voltage and BLC voltage. It can be simply expressed in this way. Please have a look at the right hand side. Here we have a C cell. C cell is actually the capacitance of our cell, and so previously here we have a half VDD and disconnected transistor. So this is disconnected, and we have a capacitor. So here we have a certain V node, and among this in this V node can be decomposed into two terms. Just normal value VDD, common value shared with this VLC plus V node minus half VDD. So since this number is equal to this number, so even when we connect these two nodes, this is just given as background value. Only this additional value will be just shared by two different capacitors like cell capacitance and inline capacitance. So this excessive voltage is corresponding to, or excessive charge is written here, and that is shared by now cell and bit line, and that is corresponding to the common voltage which can be read in our sense amplifier. So simply speaking, so let me just express this expression once again. Then our lead signal can be expressed as here the number, and this number is sometimes positive half VDD or sometimes minus half VDD. Depending on the value of a V node, it can be either VDD or 0. So we have two different cases and times. And here we have a C cell divided by the sum of a C cell and C bit line. So if we have two small number for this ratio, then actually our lead signal will be quite small. In order to keep our lead signal in a reasonable range, then actually we have to have more or less comparable value for C cell and C bit line. So, okay, so that is also design consideration. And I think that it is the last slide I have prepared, but this is just repeating the our previous discussion. In the case of leakage current, why it is important? Because in the case of our DRAM, first we write something, so logical number 1. After that, the time for this charge is completely disappeared, or this charge is solely determined by this leakage current. If leakage current is large, then it will take a short time to lose these charges. And if we have a very small, extremely small, low leakage current, then it will be quite safe even after a long time has passed. So therefore, this reduction of leakage current is so important. But here we have a quite important thing we have to understand. Now think about this array. Yes, for example, here we have 9 different devices, and eight among 9 transistors has been made quite well, so it has very low leakage current. And say that only one of them, it has high leakage current. Then you may say that, okay, there are 9 bits, so but most of them are well made, and only one is working poorly, so more or less it is okay. But it is not the situation. If we have 9 transistors and one transistor has a quite high leakage current, then think about this one. You write something 1 0 0 0 1 0 something 0 also 1 1 0. After that, after short time later, your all information will be just stored as before, but you will find that actually this original one is flipped into just 0. It means that your bit shows an error. Then how can you prevent this loss of information? Then, although your all other transistors working quite good and resist for long time, but in order to save the information stored in worst case node, we have to refresh this entire array again and again. So simply speaking, this is just a team play, not a personal sport game. So if we have 1 billion transistor, then actually the worst one determines the period of our refresh. So that is the critical point. So average is not that important. Actually, we must care about the worst case. Then how can we care about that worst case? That is really a difficult job. Okay, let me just read our slide. The charge stored in the capacitor leaks away over time. Through what? Through our transistor. So therefore, periodically we must read and refresh. And retention time means that the time interval between data refreshes. And typical worst case data retention time is about 100 milliseconds, means that 0.1 second. However, this means that we have to care about the worst device. So let me just give you an example. This x-axis is corresponding to leakage current. So if we go to this direction, then it means that we have a small leakage, low leakage current. And if we go to this direction, it shows certain cells which have quite high leakage current. And this is cumulative probability. So this is, yes, you have this one. So, I mean that here, 10 to the minus 16, then here we have a certain point corresponding to almost close to 90 or 80%. So, okay, so let me explain that in this way. So please, let me just explain this right hand side one. So here we have a retention time. Retention time is actually inversely corresponding to leakage current. If we have low leakage current, then it does not leak the charge quite fast. So it is corresponding to long retention time. So here means that this one here, this is corresponding to 1 second. and this is corresponding to 10 seconds, and this is 100 seconds. So this graph shows that only here we have, for example, this is corresponding to 0.02%. It means that when you have certain, for example, 10 okay, when you have a 10,000 samples in it, then two of them has the retention time shorter than 1 second. And if we go to this way, then here we have a 10 second, and it is corresponding to, for example, 20%. And if you have this case, if we have 10,000 samples, then actually 2,000 of them has retention time shorter than 10 seconds. So this is good, but point is, these guys here we have sometimes some set which has quite a short retention time. Then in order to save this guy, actually we have to perform quite a frequent refresh stage. So this is just a number like 10K, but you know, our DRAM has a much higher capacity in nowadays, so therefore we have to not consider just 10 to the minus 2%, but we have to care about much lower case in order to safely operate our DRAM cell. So therefore it is very important to consider this cumulative curve down toward quite several decades below than that. That is one of the most important issues in a DRAM engineer. Okay, that was quite a short and crude discussion about our DRAM, mainly DRAM cell. Okay, let me just summarize today's lecture, recorded one for our lecture 19. So let me just come back to this one. Okay, today we have a talk about memory devices. Here we have well commercialized and established memory family, and there are also alternative ones, and these ones are based on the principle like changing of resistance. So high or low, these ones are treated as logical 0 or 1, and that is called as the yes, they are based on the change of resistances. So of course, mechanisms to change the resistance are much different between them. However, anyway, all of them just based on the change of resistance. Also, we have here FRELAM, but it is a little bit different. It is corresponding to transistor structure, or some other variants are existing. And after that, we came back to the more conventional memory ones. And first, I explained the NAND. NAND has typical transistor structure, but the charge is stored in this silicon nitride layer. So by applying very high gate voltage, we can just inject electron into this storage node that increase the threshold voltage, so that is corresponding to certain writing information. That was NAND story. After that, I moved to the SRAM. SRAM, in the case, this is static, and we need 6 transistors. So since we need 6 transistors, although it has many good properties, however, in terms of capacity, it has clear disadvantages. And finally, we have a talk about DRAM. This one has only one transistor and one capacitor, and in order to maximize the uh, area efficiency, both of capacitor and transistor have been evolved quite a lot. And finally, we have discussed about how can we write something and how can we read something. One interesting thing was by doing this read operation, we are performing both actions simultaneously. Read the current value, present value stored in the charging node, capacitor node, and also write and recover that value into the capacitor. So that is done by just automatically done by just a read operation. And DRAM suffers from the significant leakage current, and retention is quite important one. And this retention is not determined by a single device or individual device, but we must see the statistical distribution of retention time. The worst one determines the overall retention time, so that's the problem. Okay, that was a simple, relatively short lecture on memory devices, and I will just upload this one for our lecture 19, and see you May 20 in second next Monday. Thank you and bye.